Welcome to your Business Calculus 5.2 lesson. Today we're going to talk about optimization. Optimization problems are problems that involve finding the absolute maximum or absolute minimum of a function. So a classic problem is you have 40 feet of fence to enclose a rectangular garden along the side of a barn. What is the maximum area that you can enclose? All right, so here we've got our barn and we've got a rectangular garden there. So we're going to let the width equal x, and we will let the length equal 40 minus 2x because we have 40 foot of fence and we've taken x here and x here. So we have the original 40 minus the 2x that we've used. All right, so we want to maximize the area. So we need the area formula, which is x times 40 minus 2x because that is our width times our length. And so that's 40x minus 2x squared. Now, if we want to maximize this, we want to take the first derivative of the area and set it equal to 0. So when we do that, we get 40 minus 4x. We set that equal to 0, and we get x equals 10. So we know that's at least where a local maximum is going to be. You also want to check the endpoints of what these values can be. The smallest x could possibly be 0, okay? But when you plug that into the area, you're going to get 0. The largest x could be is 20 because we have two of them. But then 40 minus 2x would be 0. So our two endpoints are for our area are 0, 0, and then 20, 0. So neither one of those could possibly be a maximum. So our absolute maximum must be at x equals 10. So let's look at what the area is there. Okay, so we know our dimensions now. X is going to be 10, which means that the length is going to be 20. And so the area is going to be 10 times 40 minus 2 times 10, or 10 times 20, and so we're going to get 200 square feet. So to find the maximum or minimum value of a function, you want to write it in terms of one variable, and you want to find the first derivative and set it equal to 0, and your maximum or minimum is either going to occur, your absolute maximum or minimum is going to occur either at the place where the first derivative is equal to 0 or at one of the endpoints. What dimensions for a 1 liter cylindrical can will use the least amount of material? So we want a minimum this time. So we can minimize the material by minimizing the area. Recall that the area of a cylinder is 2 pi r squared plus 2 pi rh because that gives us the area of the ends. There's two of them, and the lateral area. So we need another equation that relates r and h. So we know that the volume is equal to pi r squared h. And we know that 1 liter is equal to 1,000 cubic centimeters. All right, so for our can of motor oil, the volume is going to be 1,000. So 1,000 has to equal pi r squared times h. H is the easier one to solve for, so we'll do that. We just divide both sides by pi r squared, and we get that h equals 1,000 divided by pi r squared. So we're going to replace h, because remember, we have to have this in terms of one variable, with 1,000 divided by pi r squared. So the pi's cancel, 1 power of r cancels, and so we're going to still have our 2 pi r squared, but we're going to add to that 2,000 over r. All right, so we use the power rule here to find the first derivative. So we'll bring down that 2. 2 times 2 is 4 pi r to the first, or just r. Let's see. The second term here, we've got 2,000 times r to the negative 1. So we're going to multiply the 2,000 times negative 1. So we've got the minus 2,000. The original power of r was negative 1. We reduced that by 1. So we have negative r squared, which is r squared in the denominator. Okay, so we want to solve where this area, the first derivative of the area is equal to 0. So let's see, let's add the 2,000 over r squared to the other side, to both sides. And then let's multiply both sides by r squared. And so now we need to divide both sides by 4r, and that's going to give us 4 pi, and that's going to give us 500 over pi, and that's going to equal r cubed. So we take the cube root of both sides, and we get that the radius should equal the cube root of 500 divided by pi. And so an approximation of that is going to be 5.42 centimeters. Now, to get the height, because that is the other dimension we need, we're going to use this 1,000 divided by pi r squared equals h formula. So 1,000 divided by pi times 5.42 squared is going to equal 10.83 centimeters. Okay. If the function that you want to optimize has more than one variable, use substitution to rewrite the function like we just did. All right, so one way you can tell whether you have a minimum or a maximum is that you can do the second derivative test. If the second derivative at that critical value is greater than 0, then you have a relative minimum at the critical value. If the second derivative at the critical value is less than 0, then you have a relative maximum at that critical value. If the endpoints could be the maximum or minimum, make sure you check that. All right, guys, that's it. And so go ahead and print out your problem set. Get started on those problems. Do what you can. Come to class with questions or stop by if you have questions you want answered before class. Thank you for watching the video and have a great day.